In this video, we'll be learning a few techniques for the binomial expansion. Now, what we're going to do is we're going to use an example to begin with, which will be a plus b raised to the power of 4. And using this example, we're going to pick up on some key features that every binomial expansion will have. So let's get started. The binomial theorem tells us that a plus b raised to the power of 4 is equal to the following sum. The sum from r is equal to 0 to 4 of the binomial coefficient 4r times a to the power of 4 minus r times b to the power of r. And if we were to work through this sum, we would find that this expansion has 5 terms, which are the following. The first would be 4, 0 times a to the power of 4 times b to the power of 0 plus 4, 1 times a to the power of 3 times b to the power of 1 plus 4, 2 times a to the power of 2 times b to the power of 2 plus 4, 3 times a to the power of 1 times b to the power of 3 plus 4, 4 times a to the power of 0 times b to the power of 4. Now, what we'll be seeing in this video is how we can get straight from a plus b to the power of 4 directly to this expansion I've shown here. In other words, it's going to allow us to avoid having to worry about sigma notation and sums. So we'll be able to go straight from the expression to the expansion in one go. Now, let's see how this is done. To start, we're going to look at how many terms this expansion has. So going from left to right, we can see we have 1, 2, 3, 4, 5 terms. Yet we had raised a plus b to the power of 4. And this actually highlights the first rule that we're going to learn. The binomial expansion a plus b raised to the power of 4 has 4 plus 1 equals to 5 terms. And this will always be the case. So what I'll do is on the right-hand side of the screen here, I'll write the rules for the generic a plus b raised to the power of n. And I'll just draw a little line here to distinguish them. If I place this here. Okay. Now, a plus b raised to the power of n will always have n plus 1 terms. That's the first thing to pick up on. The second thing we're going to look at are the powers of a. And I'll just write that, powers of a. Okay, now, looking at this expansion going from left to right, we can see that the first term has an a to the power of 4, the second term has an a to the power of 3, the third term has an a to the power of 2, the fourth term has a to the power of 1, and the last term has a to the power of 0. In other words, if we write these powers out, the powers of a are going 4, 3, 2, 1, 0. And it started at 4 because we were raising this binomial to the power of 4. And in fact, this too will always occur. Given any binomial expansion looking like a plus b raised to the power of n, the powers of a, and I'll write this here, powers of a will always go n, n minus 1, n minus 2, etc., all the way down to 2, 1, 0. That will always be the case. Now, the next thing we're going to look at are the powers of b. So let's just write that. If I write powers of b, again, looking at the terms we have here going from left to right, we can see that the first term has a b to the power of 0. The second term has b to the power of 1. The third term has b to the power of 2. The fourth term has b to the power of 3. And the last term has a b to the power of 4. In other words, the powers of b are going 0, 1, 2, 3, and 4. So they're doing the exact opposite of what the powers of a were doing. So let's just add that to our list here on the right. The powers of b are going 0, 1, 2, and so on, all the way up to n minus 1, and finally n, where n is the power to which we raised the binomial. All right, we have one more thing that I want us to pick up on. We're going to look at the binomial coefficients, and I'll just underline these in gray. Looking at the binomial coefficients, we can see that the first one is 4, 0, the second is 4, 1, the third is 4, 2, the fourth is 4, 3, and finally the fifth is 4, 4. Well, hopefully you can pick up on a pattern there, and I'll just write binomial coefficients here. Binomial coefficients. If I write those out, those were 4, 0, 4, 1, 4, 2, 4, 3, and 4, 4, going from left to right. What we can pick up on here is that the top digit in the binomial coefficients is always 4. And that's because that was the power to which we raised our binomial. Remember, we're looking at a plus b to the power of 4. So that's where this 4 is coming from. And the bottom digit is just following a pattern. It's consistently going from 0 up to 4. So 0, 1, 2, 3, and 4. And in fact, that will also always be the case. Regardless of the power to which we raise this binomial, the binomial coefficient, and I'll just write this here, binomial coefficient, for a plus b raised to the power of n will always go n0, followed by n1, followed by n2, and so on, all the way up to nn. Now, luckily for us, any binomial expansion looking like a plus b raised to the power of n will always follow these patterns. So let's see how we can use these patterns to find binomial expansions. Okay, let's get started. Let's say we had to expand a plus b raised to the power of 5. Well, to begin with, it should have, following what we saw previously, it should have 5 plus 1 equals to 6 terms. So I'll just write that. 6 terms. All right, so what we can already do is say that we're going to let 6 little spaces in which we'll enter our terms. So that's 1, 2, 3, 4, 5, and 6. And remember, all of these terms are being added. So I'll just say plus, 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 and plus here. And we'll just put a little equal sign all the way in front. Now, remember, the powers of a were always decreasing by 1 unit. In other words, we can go ahead and write powers of a should go, starting from 5, because we're raising this binomial to the power of 5, the powers of a should go 5, 4, 3, 2, 1, 0. So I'm going to go ahead and add those a's in these spots. And I'll just say, okay, the first one should have 8 to the power of 5, the second should have 8 to the power of 4, 8 to the power of 3, 8 to the power of 2, 8 to the power of 1, and 8 to the power of 0. All right. Next, the powers of b. Powers of b. Well, remember we saw that the powers of b did the exact opposite of the powers of a. In other words, the powers of b should be going 0, 1, 2, 3, 4, and 5. So I'll go ahead and add those b's in there. So I should have b to the power of 0, b to the power of 1, b to the power of 2, b to the power of 3, b to the power of 4, and b to the power of 5. Last but not least, we also have the binomial coefficients. Binomial coefficients. And we know that the top digit of the binomial coefficient should always be 5, and the bottom digit should start at 0. It should then go to 1, followed by 5, 2, followed by 5, 3, followed by 5, 4. Finally, we'll have 5, 5. So let's go ahead and add those binomial coefficients. So we said the first one should be 5, 0. The second one should be 5, 1, followed by 5, 2, 5, 3, 5, 4, and 5, 5. And that's pretty much it. We're now done. What the binomial formula would have given us is exactly what we see on the screen now. And all we really have to do right now is tidy up these exponents and calculate the binomial coefficients. And when I say tidy up the exponents, what I'm referring to here is all of these. We have b to the power of 0, b to the power of 1, or a to the power of 1 and a to the power of 0. An important thing to remember is b to the power of 0 is equal to 1, b to the power of 1 is just equal to b, and similarly, a to the power of 0 is equal to 1, and a to the power of 1 is just equal to a. So let's go ahead and start by doing that. We should be writing this as 5, 0 times a to the power of 5, because b to the power of 0 is just 1, plus the second term, which will be 5, 1, times a to the power of 4 times b, plus 5, 2, times a to the power of 3 times b squared, plus 5, 3, times a to the power of 2 times b to the power of 3, plus 5, 4, times a times b to the power of 4, plus the last term, 5, 5, times b to the power of 5. Our final step would be to calculate the binomial coefficients. Now, we won't go into any detail in this video on binomial coefficients, so if you're having any trouble with those, I do suggest you watch the previous video in which we detail how to calculate them. But I will go ahead and tell you the values. This first binomial coefficient is 1, the second one will be 5, the third one will be 10, the fourth one will also be 10, the fifth one will be 5, and the sixth one will be 1. So using all of that, we could just go ahead and say, all right, this is equal to a to the power of 5 plus 5a to the power of 4b plus 10a to the power of 3b squared plus 10a to the power of 2b cubed plus 5ab to the power of 4 plus b to the power of 5. And there we go. We've just expanded a plus b raised to the power of 5 without even thinking of sums or sigma notation. All we've done here is use the pattern which always emerges in binomial expansions. Let's try working through one last example. If we were to consider a plus b raised to the power of 6. Well, in this case, I'll go a little faster, and I'll say right away, this should have 7 terms. So I'll go ahead and leave 7 spots. That should be 1, 2, 3, 4, 5, 6, and 7 spots. In between each of these, I'm going to write an addition. So plus, 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 and plus. Now, going straight to the point in this case, we know that the powers of a should start at 6 and work their way down to 0, meaning I should have a to the power of 6, a to the power of 5, a to the power of 4, a to the power of 3, a to the power of 2, a to the power of 1, and a to the power of 0. The powers of b, remember, should be doing the exact opposite. That means it should be going 0, 1, 2, 3, 4, 5, 6. So we can add those. That's b to the power of 0, b to the power of 1, b to the power of 2, b to the power of 3, b to the power of 4, b to the power of 5, and finally b to the power of 6. And the binomial coefficients, remember, should always have a 6 as a top digit, and the bottom digit should just increase 1 unit at a time, going 0, 1, 2, 3, 4, 5, 6. So that would be 6, 0, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and finally 6, 6. Now, all we need to do is tidy up these exponents. So remember, we get rid of any a to the power of 0 or b to the power of 0, and any a to the power of 1 we just write as a, and likewise any b to the power of 1 we just write as b. So that would lead to this. 6, 0 times 8 to the power of 6 plus 6, 1 times 8 to the power of 5 times b plus 6, 2 times 8 to the power of 4 times b squared plus 6, 3 times 8 to the power of 3 times b to the power of 3 plus 6, 4 times 8 to the power of 2 times b to the power of 4 plus 6, 5 times a times b to the power of 5 plus the final term 6, 6 times b to the power of 6. And the job's done. All we need to do now is calculate the binomial coefficients. And if we do that, we'll find that the first one is equal to 1, the second is equal to 6, the third is equal to 15, the fourth is equal to 20, the fifth one is equal to 15, the sixth one is equal to 6, and the last one is equal to 1. So we can write our final answer. A plus b raised to the power of 6 will equal to 8 to the power of 6 plus 6a to the power of 5 times b plus 15 8 to the power of 4 times b squared plus 20 times 8 to the power of 3 times b to the power of 3 plus 15 8 to the power of 2 times b to the power of 4 plus 6a times b to the power of 5 plus b to the power of 6. And so that's how we can find binomial expansions using the emerging patterns of binomial expansions. Remember, in none of these did we ever actually use sigma notation or sum notation. All we used to find the expansions were the patterns, and you will always be able to do this. Try a few for yourself. Try finding a plus b raised to the power 7, or 8, or 9, and you will see this method will always work.